Alright gang, here we go. This is for Chem 1, Unit 9, Part 3. We're talking about pressure. We're going to talk about gas pressures in general. Then we'll talk about atmospheric pressure and vapor pressure. Should be pretty fun. Some of it should be new, some of it should be review. Alright, gas pressure. Alright, so whenever we talk about gases, I always want you to go back to start thinking about kinetic molecular theory. Thinking about those molecules bouncing around, bouncing off each other. They go everywhere, zig-a-zag, everywhere. So gas pressure, you've probably heard this term before. Gas pressure is caused by the force of the molecules hitting the outside of the container, or the inside, the inside of the container. And so like if you have a balloon, right, you blow up that balloon and it gets bigger because the molecules of air that you've put into the balloon, okay, are actually hitting the inside of the balloon, pushing on the outside of that balloon, okay, and it's pushing and making that guy bigger and bigger and bigger. If you have something at higher pressure, it's because those little molecules are hitting harder and harder and harder, okay, and it's all based about how hard they're hitting the outside of it, okay, what's it going on, pow kapow, all this stuff, all right? And so that's essentially all gas pressure is. Pressure is also defined as the force applied over an area. So how hard is it hitting? How big of an area you're looking at? That's the pressure. All right, and we'll talk a lot about pressure here in the next unit when we talk about our gas laws, so on and so forth. All right. Empty space, so space that does not have any gas molecules at all, is called a vacuum. Okay, now one thing that lots of people get confused about is the idea that vacuum also means that there's no gravity. And that's because space has no gravity and it's also in a vacuum. But just because you are in a vacuum doesn't mean you don't have gravity. All right, we will use a vacuum pump in the classroom, and you'll actually get to see us create a vacuum in front of your very eyes, and there's still gravity in there. All right, so don't let that confuse you. All right, but if there's no pressure, you have a vacuum. Okay, that's essentially what's going on here. Atmospheric pressure is the result of all the molecules of air that are above you pushing down on you. Okay, so it's pretty wild. Up above you, you think about, there's this little Eskimo dude, and he's standing down here. There's all of these molecules of air, and they're all pressing down on him, right? They're moving back and forth, up and down, but essentially they weigh something, right? There's miles of air above you, and those little molecules of air are pushing down. In fact, over every square inch of you that's pushing on you, there's 14.7 pounds, okay, of pressure putting. So imagine picking up 15 pounds, okay, it's pretty heavy, right? But not only that, but it's over every square inch, and a square inch is not very big, you know. It's an inch, you know, based on my screen here, an inch is about that, right? And so you got a square inch would be somewhere like this, right? So for you hold out your hand, look how many square inches there are in your hand. There might be anywhere between 8 and 20 square inches on your hand. Okay, and for every one of those, there's almost 15 pounds of air pushing down. And so just by holding your hand out there, you're holding up like hundreds of pounds. Congratulations, you're superhuman. All right, or you're normally human, because we're all doing anyway. So your atmospheric pressure is the result from all of these molecules pushing down on you. All right. Now look, so this guy down here, he's a lot farther down, so there's a lot more air pushing down on him than this Eskimo that's up high. Look, he's only got this little bit sicking on him. So your atmospheric pressure decreases as you increase in altitude. So this is why when you climb, like when you go in an airplane, or you just like drive up a mountain or something like that, your ears pop because you're on the inside of your brain, your skull is a certain pressure, and it wants to equalize with the pressure on the outside, and that pressure is based on the air molecules that are hitting it. If there's less air molecules out here, or more air molecules out here than it had just a second ago, those molecules on the inside need to equilibrate themselves and become the same pressure. Okay, and so in order to do that, we pop, and it kind of opens up a little bit of our little saliva, our little ducts right here. I can't remember what they're called, and then they can equalize that pressure. All right. Barometers measure the atmospheric pressure, and there's lots of different ones. This one here is just a regular mercury barometer, and the way it works is pretty interesting. You take like a test tube, or something a lot taller and skinnier than a test tube, that's graduated, so you can actually see the scale, these values of the height here. Okay, and you create a vacuum up above the mercury, and what happens is you stick this guy in there, and so it's submerged under the mercury, okay? air pressure, just because we just explained how it's pushing down. Okay, so air pressure is going to be pushing down on this mercury, and because there's nothing up here pushing it down back against it, this mercury gets shoved up a certain height. And the height that gets shoved up here is dependent upon how heavy the mercury is and how hard it's pushing, because gravity is going to be pulling the mercury back down, but air pressure is going to be pushing it back up. And once those two forces are equal to each other, our mercury just stays still right there and it doesn't move anymore, and we can measure how high it went. And that's actually one of the scales. It's called millimeters of mercury, and it's based on just how high of a column can your pressure reach. Okay, here's another barometer here, and it's just kind of reading. These work slightly different than these guys over here, but it's pretty much the same idea. And they're just measuring how many molecules are hitting whatever it is you're talking about. All right. Now, vapor pressure, this is going to throw you for a loop, okay? Now, imagine for a second, okay, that you have a cup of water and you're at your kitchen table. You pour it out on the kitchen table and you spread it out, right? So there's just like a really thin film of water everywhere on your table. You walk away for 5 minutes. You come back. What happened to the water? Well, probably most of it's all gone. You come back 5 minutes later and it's going to be, even more of it's going to be gone. So what's happening? Well, it's evaporating. You know this. You learned this in like 2nd or 3rd grade. The water is evaporating, okay? And it evaporates because there's these molecules and they hit each other and eventually they're going to escape. And when they escape, they become a vapor. Remember, we defined vapor way back in semester 1 as a molecule that should be a gas, or some substance that should be a gas but is acting like or should be a liquid but is acting like a gas at that given temperature. Okay, and so it's acting like gas molecules. There's a water vapor in the air right now. It should be a liquid like in my water bottle, right? But it's acting as a gas. It's a vapor right now. And so we get this idea of vapor pressure. Vapor pressure is defined as the pressure exerted by a vapor above the liquid. All right, so if you have some container of water, okay, so I've got this little water bottle here. There's some water down here. All right, let me see if you can see it. I gotta look. So there's water down here. Inside of here, there is vapor pressure because this water evaporated, came up here, and now it's stuck up here, right? Because I got it capped off. Okay, so it's stuck up here. All right, and it's creating this pressure. It's pushing on this liquid in there. And that is the vapor pressure. All right, that's what we're talking about here. Okay, oops, I gotta go back over to my slide. So as we increase temperature, more and more of these molecules here can become vapor. And that makes sense because they're moving faster. And once they move faster, they can break free of these intermolecular forces that are in there. And if they can break free of these intermolecular forces, then they can become a gas. And so if we increase the temperature, that means they are able to move faster, so they can break free of those intermolecular forces. They become a gas that bounce around as a vapor. So if we increase the temperature in here, then we increase the amount of molecules that can be a vapor, and therefore more of them can be, therefore the vapor pressure increases because there's more of these molecules of vapor that are hitting the outside of my container. All right, so that's the idea of vapor pressure. Now, what occurs is pretty interesting. We can reach a point where the molecules in here, okay, that are evaporating, they'll come up here, they'll bounce around, we can't see them, but eventually they'll hit each other and slow down. And when they slow down, they'll become a liquid. Well, what do we call it when a gas becomes a liquid? Well, we call it condensation, right? And so we get to this point where we've got evaporation occurring, and then we've got condensation occurring, and then eventually we'll reach this point here that we refer to as dynamic equilibrium. So it's at equilibrium because the amount is not changing. I've had this bottle closed for a while now, okay, and so right now I've reached dynamic equilibrium more than likely in my bottle here. So in my bottle, I've got liquid water that's evaporating, and then up here I've got this gas that's condensing and it's falling back down in solution, right? And so and we've reached dynamic equilibrium. Now the trick is, and we know we're at equilibrium because this level is not going to change. I'm going to have exactly this much water in here, no matter until this bottle breaks, okay, or degrades or whatever. I could leave it sitting here for probably 1,000 years and probably be fine. But anyway, and so we'd sit here. Okay, and this level would not change. That's the equilibrium part. Now the dynamic part, well, the dynamic part is interesting. It's dynamic because it's changing. right? Just because this level is changing doesn't mean I don't have condensation and evaporation occurring. I've got evaporation occurring because I still have molecules that are bouncing around inside my liquid that are going to gain kinetic energy. And I still have condensation because I still have molecules in the gas phase up here that are going to be hitting each other and slowing down. And so I get this evaporation, condensation, and eventually I reach dynamic equilibrium where the rates of the change of one to the other is the same. So that's really the key. That's what I want you to understand is that when we've reached dynamic equilibrium, we're at equilibrium because the amounts haven't changed, but we're at dynamic equilibrium because the rate are still occurring. We still have both those processes occurring. We've got evaporation and condensation all occurring at the same time. It's very important. So let's take a gander at this thing here. So if we have some container, all right, here and we've poured it in, it's got an open container. As soon as we pour it in, we're going to have evaporation occurring. All right, so the little evaporation that's going to start occurring, we've capped it off, and right when we've capped it off, we have evaporation occurring faster than condensation. So notice that I made this red arrow bigger than this red arrow here, and that's showing you that this is it's coming out of solution faster than it's condensing into solution. And once we've reached equilibrium, these two values, these two rates have become equal to one another. Our evaporation is occurring just as fast as our condensation, and we can read this is supposed to be my pressure gauge. This is our vapor pressure we've reached. Okay, there's a pretty good video here. If you click the Google Classroom, go to the notes there and click that link. We'll watch it in class as well, but it'll help you understand vapor pressure a little bit more. They do a really good job explaining what's going on with vapor pressure. So that's it for part 3 notes. Some new ideas here. We talked about pressure, atmospheric pressure, and vapor pressure. In my experience, vapor pressure is the hardest one for students to get used to thinking about because it's hard to see, right? You can't see these gas molecules in here. They're just kind of doing their thing. It's too small. Okay. So anyway, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.